Let's say you wanted to add up the first 100 numbers like so. You could add one to each other, but that'd take too long. This problem was famously given to Gauss as a busywork exercise, but he was able to solve it in record time. His methodology leads us to Gauss's formula. What he does is takes the first and last term and adds them together. In this case, it's 101. Then take the second and second to last term, add those together, and yet again 101. The process repeats for each pair of these terms, each of them adding to 101. Since we have 100 numbers in this case, this would be 50 pairs. And each of those pairs has a value of 101. So in total, if we multiply these two together, we will end up with 5,050, which is what this is equal to. This leads us to Gauss's formula, which is seen here. Let's go over a few of the terms that are represented here. First, the S represents the sum, and the N is the number of terms. Next, we have AI and AF, which represent the initial and final term of the sequence. In the previous case we had 100 terms, the initial term was 1, and the final term was 100. When you compute this, we'll end up getting the same thing, 50 times 101, or the 5050. Let's try a different example using this concept. Here, we have a generalized sequence. It goes from 1, 2, to some unknown n. This could be 100, 1,000, a million, could just be 5. We don't know. In this case, we will add up the first and last term, we're going to get n plus 1. But notice, if I add the second and second to last term, I also get n plus 1. This is why, typically, this is written as n times n plus 1 over 2. Now, this might be a little deceiving though, because we are assuming that the first term in our sequence is going to be 1. This is not always the case. Let's try a different example to show why this general form is more important. Here, the initial term we have is 2 instead of 1. Notice that there are only 50 terms in this sequence instead of 100 like last time, since we're only considering the even ones. So when we write the sum, we're going to have 50 terms times the initial term plus the final term divided by 2. In this case, this is 25 times 102, which is equal to 2,550. Here's one more example. Right off the bat, many of you probably know that this is already equal to 15. However, you might recognize that we can't make pairs out of all these numbers. We can make a pair here and here, but we're going to be left with 3 in the middle. However, Gauss's formula still works. We have 5 total numbers, our initial number is 1, our final number is 5, and we're dividing by 2. This is the same as 2.5 times 6, or 15. However, we can also add a 0 at the front here. Now, we have 6 terms, our initial term is 0, our final term is 5, and we're still dividing by 2. This is 3 times 5, which is also 15. There are many ways of tackling these kind of sequence problems using Gauss's formula. You still have to remember that we have to have an incremental series. We can't have up 1 and then increase it by 2 and increase it by 5. It has to be the same throughout. Otherwise, Gauss's formula does not apply. That's a brief rundown of Gauss's formula. I hope it makes sense, and thank you very much.